So good morning. I am Angelica Gutierrez, co-chair of GEOGloWS, and I welcome you to the GEO 2021 Work Program Symposium. Today, I will serve as your session moderator. And to our audience, please post your questions for our presenters through the chat area, and thank you for your engagement. Over the past 4 years since GEOGloWS was launched, the initiative has grown from a vision to promote collaboration and coordination. GEO partners under the Global Water Sustainability GEOGloWS initiative, including the European Center for Medium Range Weather Forecast, ECMWF, Brigham Young University, BYU, NOAA, NASA, Servier, the World Bank, ESRI, and many more partners are leveraging advances in cloud computer, physics-based modeling, data sharing standards, and visualizations that have opened the possibility of a more holistic Earth system approach to modeling hydrology and to address a gap that no single organization has been able to address. Today, you will not only learn about the streamflow services, but you will hear from people who has been at the front of the storms and issues, making decisions on the fly, guided by the information of the GEOGloWS streamflow service. GEOGloWS provides equality as data and information has been democratized, serving all regardless of the status in technology development. We will start our session with an inspiring message from Dr. Hannah Cloak. Then it will follow by Riley Hales with a technical presentation about the system. And then you will listen about the testimonials from Honduras, a collaboration with the WMO and the Dominican Republic, Israel, Africa, and Guatemala. So thank you so much, and we will enjoy the presentations.
Hello, everyone. It's lovely to be here to talk to you. For those of you who don't know me, I'm a flood forecast scientist working across hydrology, meteorology, climate science, and disaster risk reduction. I work with a large team here at the University of Reading and with collaborators around the world, including those at the European Centre for Medium Range Weather Forecasts, ECMWF. And we're working on how we can improve the representation of water and river flow in global Earth system models. Because better predictions of where the water on our planet is right now and where it's going to be next week and even next year means that we can manage our water resources better, and we're more resilient to disasters, and we have better food security and ecosystem sustainability. We can improve livelihoods and we can save lives. So I want to start by taking you back in time to introduce you to a little girl, which is me, aged 9 years old. And every summer I went on holiday with my family to see my grandparents in Devon, which is on the south coast of England, and water always played a really big part. And if you think about your family holidays or your childhood, maybe interactions with water played a big role for you too. There are the days looking out the window at the rain, miserable that you can't go outside. There are the trips to the beach and swimming in the sea. There's paddling in rivers and ponds. I absolutely love doing that, and quite probably I have just never grown out of that. I remember feeling the current moving through the water and the patterns of the ripples on the surface, how the temperature changed from warm to freezing cold at different depths, and how the riverbed got deeper and changed shape as you moved from one bank to the other. I remember spending many a happy week swimming in Dartmoor rivers, collecting pebbles and digging and diverting intricate channels on sandy beaches. This fascination stayed with me through school and university, and while I didn't know it at the time, it helped lead me to a career as a floods researcher. I think this is because you have to spend time really looking at something to understand it. And I don't mean with your eyes, Much more important is to use your imagination. And to this day, often, as my family will tell you, I just stand by rivers, almost mesmerized by the water. I love watching the flow of the water and thinking about how all the many, many droplets that are passing by me right now, where did each one of them come from? Which pathway through the landscape did they take? When did each drop fall as rain? I like to imagine I can zoom in and see every single molecule, every droplet clearly, like a little blue petal. Because each droplet is unique and each has its own history. And if we rewind time, we can follow each droplet back to its source, so we can find out its story. You know, maybe this one fell in some of the really heavy rain yesterday in a street and rushed over the land straight into the river. Perhaps this one fell last year and has been sitting in the soil and has only just been pushed out by the force of other droplets from a more recent storm. Perhaps this one fell decades ago, maybe on the very same day that I was born, and percolated down, into the groundwater deep below the surface, slowly making its way through the rocks and finally to the river. Of course, these are only a few drops. There are billions and billions and billions of them all around the world, in the seas, so in the ocean currents, the clouds, the rivers, the lakes, all constantly moving and being buffeted around by the air, the soil, and of course by people. I find this imagining of a swirling, ever-changing world of water absolutely beautiful. This is something else I find beautiful. This is the Sentinel-1 image of the River Amazon as it leaves Peru. And this is the image I have permanently on the background of my computer screen and that I stare at all day, sometimes when I'm pretending to look at my colleagues in an online meeting. But of course, please don't tell them that. Look at the way that the river loops and meanders and threads. Pushed into extraordinary shapes by the conflicting forces of physics and chemistry and biology. I find this image a bit like a puzzle, because the closer you look, the more tributaries you can see, these tiny meandering baby rivers. Rivers are beautiful, both in their simplicity and their complexity. The swirling, the threading, the beautiful chaos of the river flow. And it's this complexity that intrigues me and inspires me every day. Think of all those tiny blue pebbles that must interact in this hugely complicated river system. It's essential to be able to work out how rivers flow and to predict when a flood is coming, because rivers are beautiful, but they are beautiful monsters. They have split personalities, drawing people in to live beside them when they're peaceful and provide food and transport, but they quickly change character and they destroy everything around them. According to the UN Office for Disaster Risk Reduction, floods accounted for 44% of all disaster events from 2000 to 2019, affecting 1.6 billion people worldwide. And they are deadly. The June 2013 floods in India led to more than 6,000 deaths. In many places, floods have been getting worse because of where we choose to live, or more often, where we've no other choice but to live. This puts people in the way of the floodwaters. We also put people more at risk because of the way we've changed the landscape. We've built whole cities on floodplains or on the coast. We've cut down trees that help to hold the soil in place. So what we really want is the power to be able to benefit from rivers when they're good, but to know in advance before they go bad, with enough advance warning to take action to protect people and communities. And that's the aim of what I spend most of my time doing, flood prediction, but it's a really hard job. As humans, we have huge societal challenges ahead of us, frightening prospects of both increased water insecurity and increased risks from floods around the world. Predicting the biggest of floods and the worst of droughts means we have to understand the behaviour, the tiniest of molecules. We must imagine the Earth as a giant system and use this to trace these billions and billions of pathways of water. We feed in the millions of pieces of data from instruments on the ground, on planes, balloons, and of course, satellites, so that we can create a picture of where all the water is and what it is doing right now, and where it will be in a day and in a week or in a month from now. And when we combine these records with the power of a supercomputer and the idea of the Earth system, it's possible to make global forecasting models, providing flood forecasts for all the major rivers on Earth. And 10 years ago, this was not possible. But now we have the GEOGloWS system, we have the GEOGloWS ECMWF streamflow services, we have global real-time flood information that can be used locally to take real on-the-ground decisions to help reduce the risk to people and livelihoods. So from this global picture, let's zoom in a little. This is Mozambique, a beautiful country, but one with a huge percentage of its population living in extreme poverty. The coast of Mozambique is regularly battered by tropical cyclones. Here in the Northern Hemisphere, around the Atlantic, tropical cyclones are of course better known as hurricanes, which is what they're called when they hit America. But in Africa, they're called cyclones, the most powerful storms in the world, hundreds of kilometers across and causing strong winds, storm surge from the sea, and heavy, heavy rains that lead to flooding. The warm waters of the Indian Ocean fuel these storms as water droplets continuously evaporate and build up the swirling clouds and the structure of the storm. In March 2019, a huge tropical cyclone called Idai hit Mozambique. And then just a few weeks later, another huge tropical cyclone called Kenneth slammed into the country. Hundreds of thousands of people were in immediate danger. And I worked as part of a team using the GEOGloWS global flood forecasts to help provide information to the UK government and to humanitarian partners, such as the Mozambique Red Cross. We analysed the tropical cyclone track forecasts, looking at where and when the cyclone might make landfall, but also where it might be dumping all the rainfall that it was bringing with it. Really importantly, we could say where and when the flooding was likely to occur and where people were most at risk. And providing this early warning means that actions can be taken to prepare for the devastating impacts of huge floods before they happen, rather than just dealing with them after they have happened. People can be evacuated. Rescuers and equipment can be moved to the right place and put on standby, and lives can be saved. But of course, this is just the beginning, because we're just learning about how global services can best support lesser developed countries. And with the combined power of Earth system models, Earth observation products, local expertise, and an understanding of how water and society interact, we could do so much more. And also, these types of global services are only going to become more important as climate change makes extremes of weather more extreme than we're used to. It's a complicated picture. It's not one that we understand fully. And in the past, I think we've hesitated to say that climate change causes a particular flood to happen, because rivers and land have flooded since before humans existed. But we can say now, with increasing certainty, that you can see these human fingerprints in the form of climate change and its impacts on our planet, on many of the floods around the world. And what's very clear is that we need to be much better prepared for more intense and more frequent flood events in the future, as well as more severe heat waves and fires and droughts. So very often droughts are characterised by a lack of rain, leading to a lack of flow in the river, which leads to crop failure and water shortage. But humans play such a crucial role in droughts and water insecurity, and we know that different social groups diversely interact and co-evolve with our human water systems. I work with a brilliant researcher, Elisa Savelli at Uppsala, who has been exploring the major water crisis known as Day Zero that shocked the city of Cape Town in South Africa in 2018 following a prolonged drought. She found two families that truly embody the different conditions of water access among Cape Town residents during the drought, and who had wholly different experiences of the water crisis. In Langa, which is a coloured township, she spoke to Kayla, and she tells the story about how in February 2018, in the early evening, she was about to rinse off her hair, but not a single drop of water comes out of the shower head, because she had finished the limited amount of water that her large family was allowed to consume on that day. Whilst at exactly the same time, in Bishop's Court, which is about 14 kilometres southwest from Langa, the Duplessis family is watering the garden with water from the borehole they had recently drilled. Now, we can't blame the lack of rain for these differences. Cape Town's political legacy has encouraged unsustainable levels of water consumption amongst the white elite and tolerated chronic water insecurity amongst Black informal dwellers. So this is another opportunity for GEOGloWS. If we can better identify those mechanisms within society that determine what water is secured and what human-water interactions and dynamics will be sustained over time, we can better inform policies that reduce inequalities in water access and unsustainable water use. To me, the world's rivers and groundwaters and oceans and clouds will always be beautiful monsters made up of billions of precious blue pebbles, but with a bite that can hurt in water crises, devastating floods, and environmental damage. But little about this bite is natural. It's because of how we as humans interact with the water cycle. GEOGloWS has a really unique and crucial position here. The strength of collaboration, a focus on openness and sharing, and the ability to integrate big data, global Earth system infrastructures with global policy, local expertise, and most importantly, local requirements. Now, I have only one sneaky request before I stop. I make this plea to politicians, mathematicians, poets, and school children alike. Next time you happen to be next to a river, take a moment to stop and look. And go beyond the mass of swirling water before you. I want you to zoom in and look for those blue pebbles and ask yourself, where did they all come from? When did they all come from? And where are they all going to? Thank you for listening.
Hello everyone, my name is Riley Hales. I'll be presenting a brief introduction to the GEOGloWS ECMWF streamflow model. In order to really understand why the model is unique and why it's important, I'd like to start at the very beginning with why we need streamflow data. And really the world needs better water data of all kinds: groundwater, streamflow, lakes, water quality, and so on. We live next to water. We vacation to go see it, we drink it, we need lots of it, yet sometimes we get too much of it. Flooding is one of the most costly natural disasters every year. It takes many lives, countless dollars in infrastructure damage, lost homes, crops, and so on. Conversely, though, many people live far from water. These people are more worried about, am I going to have enough water? They're more concerned about drought conditions. And while these are both extremes on the need for water, the solution to both of these scenarios is you need to have better water data to inform your decision-making process so that you can be prepared for either the flood or the drought to make sure you have enough water. Traditionally, the way that we provide this data is shown here on the top row of the slide. We'll take global data sets, expertise, computing resources, the human resources, and provide that to an organization or government that needs to build a hydrologic model. And this is really invaluable, provides lots of benefits, and traditionally this is how the interventionary programs into the least developed parts of the world have worked. And while it's provided a lot of benefit, it hasn't produced the long-term sustainable change that we would have liked to see. So what we've tried is shown on the bottom row of the slide. Rather than build a separate model everywhere, we've experimented with taking the global data sets, human expertise, compute resources, and all that, building a global hydrologic model, and then providing a global service rather than data sets to each of these organizations that need data. And we think this has the potential to provide really sustainable benefits in the long term, since you only have to maintain a single model and you can optimize it and get cost savings that way. For the purpose of this presentation, there are really two challenges to make this work. First is, can you build a model that's that large of scale, that's sufficient quality? And then the second challenge is, can you make it accessible? Can you build enough useful services that it's providing the benefit that we need it to? So I'll start first with describing how we built the model. We started using the best available data sets and technology and building on top of that. So we took the ECMWF land surface model data. This is the same data that powers GEOGloWS and ERA5. It produces these GEOGloWS maps that you're probably familiar with. This is a raster data set, meaning it's produced on a grid, like I've shown here with the colors. We second produced a watershed network. This is a geographic data set where watersheds are represented by polygons and the streams by lines, as I've shown in this simple figure. And this covers the entire globe. It's got about 1 million stream reaches, and the average area for each of the stream subsegments is 150 square kilometers. And the fact that it covers the whole globe and has a uniform set of metadata and a unique numbering system for each stream segment makes it valuable in its own right. But then we combine them together using standard GIS operations, and we can produce these tables where we know how much of each cell is in each watershed and how much runoff is expected to be in each of those cells, so we can crunch the math and figure out the volume of water that ends up in each of the watershed subsegments. So then when we put all of these subbasins together into the larger stream network, we can route from one subbasin to the next using the Muskingum routing, and until all the water reaches the outflow of the entire watershed. What this produces is two principal data products. The first is a historical data set. It's deterministic, so it just has one data set, and it goes from 1979 to the near present, with just a few months of lag. So it's more than 40 years of streamflow data. And the second data product that we produce is a forecast. It's stochastic or probabilistic, meaning we make 52 different predictions, and we generate plots like shown below. And we produce a new one of these forecasts every day. It covers the next 15 days. So this is a lot of data, especially when it's done at a global scale. And we need ways to easily interact with that much data, which leads us to, how did we make the model accessible? Well, there are two ways. We have a data service and a mapping service. First, the data service. We built a REST data service, which means that you can retrieve just subsets of the model by building simple URLs like you would to go to a website. So in this figure I've got on the left, we have a hydrologist who needs data, and we've got data from the GEOGloWS model sitting on the cloud. She can open up her computer, use her web browser, build a URL using the patterns that we've documented. And then rather than get back an entire global data set, which is many, many gigabytes and would be a lot of work to parse through, she can get back just a CSV of the portion that she's interested in, something that corresponds to her river segment. So this is really versatile, and it's really powerful to just be able to get the information you need this way. It's accessible through many programming languages. You can get it in Python, R, MATLAB. You can get it in Excel or Google Sheets. Really anywhere you can get on the internet, this is accessible to you. We've also developed a Python package which automates building the URLs, downloading the data, and also provides you tools to generate some plots and do additional post-processing of the data. The second way that we make this data accessible is through a mapping service. And so this is a view of the global mapping service, and it was built with our collaborators at Esri. And you'll notice that there's some custom styling going on. The line thicknesses change, and there's also coloring as you go to different rivers around the world. And this mapping service corresponds to the most recent forecast. So based on our forecast data, we can change the thickness of the line, like I've got shown on the top right of the slide, the thickness to match the volume of water moving through the river at that point. Then the color indicates whether or not we expect that river to exceed a return period threshold. And we've also generated a variety of maps and color schemes to make this easy to access online. And this service is available for free using Esri's Living Atlas. So any web map or GIS software should be able to ingest this mapping service quite easily. And I mentioned this is animated, so I've got a demonstration video of the animation. If you'll pay attention to the bottom of the video, you'll see a time slider. And as the time is advancing, the coloring and thickness of the line changes. And so this was a really large storm in Peru. And so we have some purple, red, and yellow coloring and various line thicknesses that are changing throughout the forecast period. We can watch the water propagate down the stream network. So we've got a data service and a mapping service. We combine those together to create a authoritative interface to the model. We call this the GeoGloWS Hydro Viewer, and it's a web app available at apps.geoglows.org. So I'll play a demonstration of this as well. And so you'll notice that same map that I've been showing you as before. And so the user's panning in, watching the animation, using the controls at the top left to move through the animation period. And when you're satisfied that you've looked through the animation how you want, you can click on a river. And then using that data service that I mentioned, the app retrieves data to create these plots for you. You can toggle on and off the different components of the forecast. And when you're done, you can download the data through the app, or you can go back to using the data service according to your preference. So we're currently working on many projects to improve the model. We have performed already a historical validation and forecast skill analysis, and we're working on the reports for that as we speak, so that's forthcoming. We've documented through that process that there's some bias in the model, as you would expect in most engineering models. So we've developed tools to correct the bias where we have local data. Using the forecast data as a flood early warning system, generating flood maps, applying it to droughts. These are all areas that we're interested in pursuing at various stages of the research process. And we've also compiled a repository of training tools, workshops, presentations, code notebooks, and so on that help people use the tools into a single website, geoglowstraining.readthedocs.io, so that there's a central repository for information on how to use these services and make the model accessible. Thank you very much. I look forward to taking your questions.
Hola, muy buenos días. Soy Manuel Conde Cuevas de la Empresa Nacional de Energía Eléctrica de la Unidad de Hidrología en Honduras. Honduras es un país ubicado en Centroamérica que fue abatido por dos huracanes en el mes de noviembre del año 2020, el huracán ETA de categoría 4 el 2 de noviembre, el huracán Iota de categoría 5 el 16 de noviembre. De estos dos huracanes, pues teníamos falta de información a largo plazo de los pronósticos de aportes que nos podrían brindar a nuestro país. Uno de los zonas más vulnerables del país es conocida como el Valle del Suna, una zona bastante poblada con 2 millones de personas que produce alrededor del 65% del Producto Interno Bruto. Hacia esta zona drenan alrededor de unos 22.000 kilómetros cuadrados de 4 ríos en las aguas arriba. Únicamente una de las cuencas es regulada por una central hidroeléctrica, la Central Hidroeléctrica El Cajón, que controla alrededor del 38.7% de esa área. Esta central hidroeléctrica, Francisco Morazán, a la cual pertenece la empresa a la cual represento, durante el huracán ETA, el primer huracán que nos azotó, pues tuvo la capacidad de retener la mayor cantidad de agua durante el huracán y maximizar la producción de energía, evitando drenar todos estos caudales hacia el Valle de Sula y evitar catástrofes. De las herramientas utilizadas durante el huracán ETA, pues utilizábamos el modelo CAFG, modelo centroamericano, con horizonte de tiempo de 6 a 24 horas, y el modelo WRF con horizonte de tiempo a 3 días, pero lo cual no nos daba resultados satisfactorios, por lo cual no lo utilizábamos. Para ese momento, durante el huracán ETA, pues no conocíamos los pronósticos del GEOGloWS, sino que fue a través de nuestros contactos con Américo Geo que tuvimos el primer acercamiento. Sin embargo, después del huracán Iota y conociendo el anuncio de que se aproximaba otro segundo huracán para noviembre de 2016, la situación para la toma de decisiones se complicaba. Entonces era necesario tener a largo plazo información de pronósticos, por lo cual decidimos verificar qué estaba pasando o qué había sucedido con el GEOGloWS, haciendo una validación con los datos observados en nuestra central o nuestro embalse. Lo que esta validación pues nos ayudó a permitir a tomar la decisión de que sí vamos a utilizar los pronósticos del GEOGloWS, y en noviembre de 2012 empezamos a hacer los primeros análisis con el pronóstico del GEOGloWS para saber qué nos pronosticaba para la tormenta o huracán Iota. Con estos pronósticos pues hicimos las primeras proyecciones de nuestros niveles o de nuestro embalse, y nos ayudó a tomar la decisión de que era necesario realizar descargas porque no teníamos la capacidad necesaria para almacenar toda el agua que nos iba a dejar el huracán Iota durante su paso. En noviembre de 2014, pues cuando no existía fenómeno abatiendo al país, tomamos la decisión de hacer estas descargas de manera controlada hacia el Valle de Sula, evitando catástrofes mayores, y se lograron descargar 185 millones de metros cúbicos para producir un espacio de almacenamiento adicional que iba a almacenar el agua que nos dejaría el huracán Iota. Igualmente, durante el paso del huracán Iota, se hicieron validaciones en tiempo real de lo que estaba sucediendo versus el pronóstico. Esto adicionalmente nos ayudó a tomar nuevas decisiones, y se tomó la decisión de cerrar las compuertas de descarga para evitar aún más aportes durante el huracán Iota hacia el Valle de Sula. Todas estas acciones ayudaron a tener beneficios importantes porque se evitaron mayores daños socioeconómicos y pérdidas en el Valle de Sula, y ayudó también a la coordinación entre los sistemas nacionales de emergencia local y los comités permanentes de contingencia, con información que la ENE, la empresa a la cual represento, brindaba a ellos basado en el GEOGloWS. Gracias a nuestra exitosa gestión, la población en general y las autoridades de nuestra empresa y las autoridades del país, pues reconocieron nuestro esfuerzo, y al final nuestra empresa y nuestra represa fue reconocida como el héroe silencioso del Valle, ya que logró retener gran cantidad de volumen de metros cúbicos que no fueron descargados al valle. Muchas gracias. Manuel Conde, de Honduras.
Greetings, good morning, good evening, good night. My name is Calvin Swara. I work at the Regional Center for Mapping of Resources for Development, and I work as thematic lead on water and hydroclimatic disaster. I would like to share with you what to do in the region, especially the use of GEOGloWS, stream flow focusing service, to address the issues of the transboundary in our member states. Data scarcity has been a problem in the region, and it impedes certain progress in monitoring the water resources. And therefore, what we do is to support the applications of Earth observation data for stream flow monitoring and focusing, to address three main issues: to make the data on stream flow data available to the management and also for decision making, to support water resources planning, allocations, and management in the region, and lastly, for the aid flood focusing for disaster risk reductions. How we do this? We do it through the co-development of tools and platforms with various organizations and mandated agency. We train capacity build within our member states, and we partnership with relevant organizations, typically in point in which we requested the BYUE to facilitate in terms of capacity building on the GEOGloWS stream flow service. We work in the Eastern and Southern Africa countries, where we work with different partners. On issues of the transboundary management or being addressed by the GEOGloWS, A case in point is a project we are doing in Malawi, establishment of a community-based flood early warning system in 8 selected flood-prone districts, and working across 28 rivers. One of the rivers that we're working on is called Songwe River. It's a transboundary river that is shared between Tanzania and Uganda. And it is being managed by a commission that is set up by those two countries. And the key challenge here is, mostly is flooding. And the elements that are at risk are mostly the downstream communities that occupy both sides of the riverbank in Tanzania as well as in Malawi. The data availability to support the disaster risk monitoring, the disaster risk reduction through monitoring is a challenge. Therefore, through the funding from the UNDP, we implement an establishment community-based early warning system. And the approach we've adopted is to use an hybrid system in which, a telematic equipment will be able to give us, flood information, monitoring the flood waves at the higher upstream, and provide that flood warning information within 2 hours. But also we leverage on the strength of the GEOGloWS to give us a streamflow forecasting with elements of days, 10 days, and 5 days, and be able to characterize this. So in doing this project, we use GEOGloWS provisions of the 30 years data that they provided to determine our threshold level. This GEOGloWS data was bias corrected with observed and also implemented within the telematic water level monitor that's located in the downstream. The element of the community here is being the caretaker who is empowered to make certain, trigger alarms to the downstream community whenever a threshold is exceeded. And these two platforms offer us a very good opportunity, given the accuracy and the reliability of the flood early warning information that can be provided from the downstream community to reduce the risk, of disaster in those locations. How we do this? We do it through the partnership of various organizations and the government departments, as well as the university that are working with the region, as well as also the community. And what we aim to achieve from this, is to make the streamflow data available for decision making process using this hybrid system, and also improve flood risk and disaster strategy to the downstream community, where they'll be empowered to make certain decisions regarding how to respond to, an impending disaster. And improved skills and the capacity building for various government organizations is very important, as much as we would want to transfer the telematic equipment as well as the GEOGloWS, but we also have to build the capacity. So in the long run, an improved capacity building within these government organizations is very key in disaster risk reductions and the provisions of the data that they need to make this particular informations. With that improved theory, we are thinking that probably, a disaster such as this might not, occur with the fatality that has been in the past, given the available data that's provided with the GEOGloWS and the telematic-based equipment, and also the lead time in which, the various organizations, humanitarian organizations, and the government agency can respond to an impending flood event. And with this, we impose the community lives will improve, and also the disaster will reduce significantly in these areas. Thank you so much.
Buenos días o buenas tardes a todos. Soy Tania Gaspón, hidróloga y responsable del proyecto en la OMM. El tema de mi presentación es sinergia entre sistemas hidrometeorológicos como apoyo a la toma de decisión en República Dominicana. Inicialmente me gustaría enfatizar que el OMM impulsa la cooperación internacional para mejorar la prestación de servicio y uso de servicios meteorológicos, climáticos e hidrológicos de alta calidad para el beneficio de sus miembros. Son muchas las iniciativas, programas o proyectos que permiten establecer colaboraciones enfocadas en mejorar estos servicios. Un ejemplo de esto se encuentra en la República Dominicana, en la cual actualmente la OMM, en colaboración con el Servicio Hidrológico Nacional, INDRI, y el Servicio Meteorológico Nacional, UNAMED, se encuentran implementando y desarrollando un sistema de pronóstico integrado para producir impacto en áreas locales en sinergia con diferentes sistemas existentes. El desarrollo de este sistema se encuentra dentro del marco de un proyecto que está financiado por Environment and Climate Change Canadá. Este es un proyecto regional en el cual se busca mejorar la resiliencia ante eventos hidrometeorológicos extremos a través de la mejora de sistemas de alerta. República Dominicana ha sido impactada por diferentes tipos de inundaciones que han causado desgastes y daños a la población y también a nivel material. En la República Dominicana han sido muchas las iniciativas y programas que han permitido el desarrollo de sistemas para monitoreo y apoyo a los pronósticos meteorológicos e hidrológicos. Por ejemplo, en colaboración con Meteofrance, la OMM ha implementado el Severe Weather Forecasting, que le permite al Servicio Meteorológico tener acceso a productos de pronóstico de precipitación a alta resolución. También el Instituto Meteorológico de Cuba ha apoyado al Servicio Meteorológico para el desarrollo de pronósticos de alta resolución. En cuanto a sistemas para el apoyo a la previsión de inundaciones, la República Dominicana cuenta con Flash Flood Guidance System, CIFI y GEOGloWS. Estas iniciativas o estos diferentes sistemas que han sido implementados actualmente están sirviendo de base para la creación de un sistema integrado para pronóstico de inundaciones en cuencas pilotos. Este sistema integrado, aquí en esta presentación, en esta slide, perdón, les voy a mostrar un pequeño resultado de lo que es el sistema integrado para pronósticos de inundaciones fluviales. Aquí podemos ver que este sistema ha sido construido tomando como base el sistema de pronóstico global GEOGloWS. Y este sistema ha servido para visualizar y también facilitar el intercambio de datos para el desarrollo de pronósticos en cuencas locales. Este ejemplo está basado en la cuenca del Yaque del Norte. Y también ha permitido realizar conexiones para facilitar la visualización de pronósticos de impactos. ¿Cuáles son los beneficios obtenidos en este caso de estudios? Pues tenemos que se ha mejorado el intercambio de datos meteorológicos e hidrológicos para apoyar el desarrollo de sistemas de pronóstico a través de GEOGloWS, el cual es el sistema de monitoreo hidrológico del OMM. También ha permitido promover el uso y la validación de sistemas meteorológicos e hidrológicos ya existentes y también de facilitar el acceso a productos a través de nuevas interfaces. También ha abierto la posibilidad para el desarrollo de nuevos sistemas de monitoreo y pronóstico a través del uso de soluciones libres, de soluciones open source. Y ha facilitado la implicación de los agentes del Servicio Meteorológico e Hidrológico en el desarrollo y la implementación de este sistema. Uno de los grandes beneficios de este proyecto, de esta colaboración en República Dominicana, es que ha servido de lección aprendida para estructurar nuevas colaboraciones. Por ejemplo, una de estas colaboraciones que utiliza este proyecto como piloto es HydroSOS, la cual pues es una iniciativa del OMM centrada en realizar un estatus hidrológico y analizar las perspectivas de las tendencias hidrológicas. Aquí en este slide pueden conseguir mayor información sobre los diferentes objetivos del HydroSOS. Este pequeño slide resume la colaboración que se ha llevado a cabo en el marco de este proyecto. En este proyecto hemos implicado al Servicio Meteorológico Nacional para la validación de productos ya existentes. Hemos implicado también al Servicio Hidrológico Nacional para facilitar lo que son instalaciones de sistemas locales, medidas sobre el terreno, organización de formaciones, etc. También trabajamos con Brigham Young University, que está desarrollando todas las soluciones utilizando como base el sistema GEOGloWS que ya había sido desarrollado en República Dominicana por su equipo. También estamos trabajando, como lo dije anteriormente, con el ISMED de Cuba, que está facilitando, apoyándole a UNAMED a realizar todo lo que es interpretación y mejoras de pronósticos meteorológicos. Estamos trabajando con el equipo de CNR2 para la implementación de PUS, con Acuaveo para la mejora de bases de datos y con el Centro de Formación de Argentina para todo lo que corresponde a la coordinación de trainings. También hemos beneficiado una colaboración con IDB para adquirir el sistema que nos permite realizar los pronósticos de impacto, Hydrobit Float. Les dejo aquí esta imagen que representa uno de los trainings que ha sido coordinado recientemente por los consultores del OMM en el marco del proyecto. Gracias.
Hello, everyone. My name is Dr. Amir Gibati, and I'm working with the Israeli Fire and Rescue Authority and the city of Tel Aviv from the Tel Aviv University as a consultant regarding flood forecasting and urban inundation. And today I want to present it shortly a decision support tool that we developed for those authorities in Israel for flood risk assessment. So it's actually an early warning system for flood and inundation. And the example, the case study would be the city of Tel Aviv. So this is the city of Tel Aviv. It's in the central part of Israel, on the shore of the Mediterranean. You can see on the left the Mediterranean. Just a few details regarding the city itself. So around 500,000 people are living in Tel Aviv, but around 4 million are in the surrounding metropolis area, this is the biggest metropolis area in Israel, the capital of the finance capital, and most of the people are working in this area. So you see here in the map, it's in the center of Tel Aviv, lying in the Mediterranean, and the city itself is suffering from flood and urban inundation, and it's a result that is meeting poor drainage developed urban area. And in addition, there are two rivers that cross the city, and in a situation that you have intense rainfall plus high water elevation in the river, then you get severe flooding. So this is the case in Tel Aviv, and we want to be ready for those events when we have intense direct precipitation in the city itself. And in addition, water coming from upstream from the basin, we showed before those two rivers, we named Ayalon and Yarkon. So we actually started to use the GEOGloWS system on those rivers. And we are providing the responsible for decision making. So we started to use it from last year, last rainy season in Israel. And during November and December of 2020, actually, we had a few flood events in those basins. You can see in the bottom those flood events, around 4 peaks. And on the left, you can see the river crossing here. So we use the system, we use the inflow forecast in addition to rainfall forecast that we have from the National Weather Service. The combination of those two of them actually allowed the authorities and the decision maker, like the people that run the drainage, they got this data. By getting the data into insights, they could take action to be proactive and to be better prepared for those flood events. So I can say in confidence that tools like the GEOGloWS ECMWF stream flow system are very effective. They are saving property and life once you know how to use them in the right way. Just one technical slide to show how it goes. So there is a dashboard at the operational center at the city of Tel Aviv and also at the Fire and Rescue Authority. They are the first responder that need to take action. So on the left side, we can see precipitation and meteorological forecast. You see the rain intensity in blue. And on the right side, this is inundation map that we create for them. So the red spots represent extreme flooding areas that are going to suffer from extreme flooding. But this is not enough because it's only direct rainfall. It's coming from very high resolution numerical the WRF model. We use the geo system in order to embed a combination of rainfall and streamflow forecast is the solution for the city itself. So you can see in black, this is the area where the flow is going to generate it, and you can see the hydrograph, the expected hydrograph, thanks to the geo system. On the bottom slide, you can see the assessment that we are doing, the effect of the flood in the low area in the city. So we identify in advance, like around 10 locations that are the most sensitive to flooding. And once we have the meteorological forecast plus the hydrological forecast coming from the geo system, then there is a solution. You can be prepared. What does it mean? What action we are taking? We are bringing more crew to the field. The fire people are ready for evacuation. They can close streets. They can bring pumps in advance. So then their action are much more effective. So first, to summarize, what we saw in this short speech is an example for the city of Tel Aviv, Mediterranean area that suffered from flash flood, how information system like the GEO can help authorities to be better prepared to take proactive action. Once you have the data and you know how to take insight out of that, because the data itself is not enough. So you need to understand the severity of the flood, the return period, how rare it's going to be, together with other information like direct rainfall. You can be better ready, and then you can have better preparedness for the citizens. So we're really thankful for the system. We would love to keep cooperate and be part of this amazing system. And thanks everyone that created this geo system. This is it from Tel Aviv.
Hello, my name is Alma Meyer. I'm an undergraduate research assistant at Brigham Young University studying civil engineering. Today I'll be presenting on how the GEOGloWS ECMWF Streamflow service was used to address water quality issues in Lake Atitlan, Guatemala. Lake Atitlan is a pristine endorheic lake in the volcanic highlands of Guatemala. The lake is a vital part of the economy of the surrounding towns. It is the second most visited tourist site in the country and the source of drinking water for about 400,000 inhabitants. Many also say that it's the most beautiful lake in the world. However, in recent years, Lake Atitlan has been contaminated by sewage and agricultural runoff. This has caused algal blooms that first appeared in 2009. At the 5th World Water Forum in Istanbul, Lake Atitlan was declared Threatened Lake of the Year 2009. This set of satellite images shows the algae blooms swirling across the lake from October to December of 2009. These algae blooms now unfortunately occur almost yearly, according to the analysis led by Servier. This issue is only worsened by increasing population due to tourism. There are no sewage treatment plants in the region, so the lake is the ultimate receptacle of all waste. Through a project financed by the Inter-American Development Bank, the Sustainable Management Authority is working to strengthen local solid waste management systems to change the practice of waste discharge into Lake Atitlan. This is one of the main causes for eutrophication. In response to growing concerns over the future of Lake Atitlan, researchers at NASA Servier have been working to use satellite images to understand and address the lake's water quality. The Servier Science Coordination Team, led by Africa Flores and with the support of National Geographic and Microsoft, is developing an algorithm that predicts when algae blooms will occur using satellite imagery data, artificial intelligence, and machine learning. But to make the algorithm work consistently, they were lacking data for one important variable, daily discharge volume into the lake. That data was originally obtained from the Global Land Data Assimilation System, or GEOGloWS, but a few months before their algorithm was ready to share with local stakeholders, GEOGloWS stopped producing the data at the frequency that they needed to produce useful forecasts. Thus, they were in need of a hydrologic model of the Lake Atitlan watershed to get the streamflow data needed to complete the algorithm. Servier's science coordination team approached researchers at Brigham Young University, who helped develop the GEOGloWS ECMWF streamflow service. The streamflow service's high resolution made this a great alternative to provide local data for Lake Atitlan. With the help of my colleagues at BYU, I was able to write a script that retrieves the streamflow service's forecast data for the Lake Atitlan watershed and converts it into daily discharge volume. The script first retrieves the forecast using the reach IDs for the 3 rivers shown here, the 3 rivers flowing into the lake, and then here are a few forecast hydrographs for these rivers. Since Servier's algorithm required discharge volume, we integrate the streamflow hydrographs using the SciPy Python package. This package performs trapezoidal integration, as shown here, and this script was easily incorporated into Servier's algorithm to predict algae contamination in Lake Atitlan. The forecasting system will aid organizations such as the Authority for the Sustainable Management of the Lake Atitlan Basin and its environment, the Guatemalan Ministry of the Environment and Natural Resources, and the Atitlan Study Center at the University of the Valley of Guatemala, as they develop and implement solutions to the contamination problem. These solutions will benefit the 368,000 inhabitants that rely on Lake Atitlan as a critical part of their livelihood. Servier's algae bloom analysis has already informed 2 key policy documents published in 2011, and this new algorithm will further aid decision makers as they address the water quality of Lake Atitlan. Just the simplicity alone of the Python script testifies to the success of the streamflow service. Although the model is global and consists of more than 1.5 million rivers, it is accurate enough to be a powerful tool at a local level. The GEOGloWS ECMWF streamflow service gave Servier's science coordination team the data that they needed to complete their algorithm while maintaining its resolution. They were able to retrieve data for a relatively small watershed and solve a localized problem, helping them fulfill their mission of connecting space to village. Thank you all for your time.
Hello, everyone. It's lovely.
Thank you to all our presenters for the enlightening presentations. Thank you to Dr. Hannah Clark for such an inspiring keynote. I'm going to read some of the questions that have been posted in the chat area. And one of the last questions, I guess very relevant to the last presentation we saw, was, are there plans to extend the model beyond stream flow to also include water quality? So I think that as Jim Nelson answered here, the most important piece is that the open service, as it was demonstrated in the last presentation, is showing how many other applications can be actually connected to the stream flow forecast. Applications perhaps in agriculture, water quality, insurance, and so forth. So this would be, this is just an example of how this service can be extended. Let me see there was another question that came privately, and I would say, it says, what other areas is the system being used? So Dr. Nelson,
say that again. What was the question?
How many other areas or what countries, where do we have, where are we working with applications?
Yeah, we're working pretty much in every continent, in Africa, in South America, in Colombia, and Peru, both the hydromet services there in the Dominican Republic, in several countries working with SICA and CRH in Central America, several of the other countries. We saw Honduras and Guatemala in these presentations, but also in Panama, El Salvador, Costa Rica. So it's being used in more and more places all the time. We're trying very hard to get work published and as Riley presented, information out there so that others can more easily adapt. We're working with Harsh and the World Bank in India, in Afghanistan. So many different regions where we can help supplement and build capacity.
Thank you. So we have arrived, this is the end of our session. Encouraged to submit your questions. You can reach us out at geoglows.org. And thank you so much for your participation this morning. I hope that this session was inspiring, and to everyone who's doing water and forecasting and models, let's get connected. Let's work together. This is an invitation to all the organizations to work together in advance in assisting the so many needs that we have in our planet. So thank you and have a wonderful day.